What I'm going to do is try to give you a sense of the modern theory of core collapse supernova explosions, and that there's been significant progress. In fact, we're in the middle of a revolution in understanding these objects that has taken decades to achieve. It's just going to be the tip of the iceberg, though, and of course that tip and the iceberg depend on a team and resources, and I'd like to acknowledge the resources, and in particular the team: David Vartanian, David Radice, Hiroki Nagakura, Victoria Morozova, Aaron Skinner, and Josh Dolance in particular for this work. I'm going to give you some text in the beginning, some basic background, then I'm going to get to the eye candy. The basics are, and I'm sure many people in the audience know about this, you start out with a massive star's core that evolves to the Chandrasekhar mass. It collapses, it bounces, launches a shock wave, and there's been a problem because that shock wave, pretty generically in these simulations, stalls. And so the idea, what we need to do is to revive that shock. It involves nuclear physics, the equation of state of nuclear matter. It involves neutrino matter interactions. The radiation in this context is neutrinos. Neutrino energy deposition is crucial to reigniting the explosion. Turbulent pressure, because this object behind the shock is turbulent, is crucial as well. And the turbulence has to be done in multi-D. And so we've been waiting to get the proper neutrino energy physics and the turbulent pressure, the multi-D capability, and we are now at the point where we can reasonably conclude that we have the necessary realism incorporated in the codes. Without any artifice, without any fudging, we get explosions almost generically. We get explosions in 2D with axisymmetry as well as 3D, and I'm going to be focusing on the 3D. The phenomenon is a critical phenomenon, so you can address it qualitatively in terms of bifurcation theory, but the multi-D is essential. What's new is being able to do the turbulence properly. Over the last many years, we finally enabled multiple 2D simulations, which allowed us to make mistakes, but at the same time, we could do maybe one 3D simulation in a year. We are now in the epoch where we can do multiple 3D simulations in a year, and we can afford to make one or two mistakes, which wasn't possible. And in order for there to be progress in this science, we have to be able to do multiple simulations to look at the parameters and to educate the community. We are now doing that. There are various particulars that are important, but one of the most important things is the codes that are available and the resources that are available. The code that we're using is Fornax, which we developed from scratch for this problem, that can do 1, 2, and 3D multi-group radiation hydrodynamics. It will do magnetohydrodynamics in about a year. It has various bells and whistles, but it has enabled multiple 3D simulations because it is explicit, not just in the hydro, but in the transfer, because the radiation moves at about the speed of light, and that's similar to the speed of sound in our problem. And so we can do the Riemann-Godunov-like problem for the solution to the transport operator explicitly, doing the local calculations implicitly, so that you have the local implicit updates. So that's perfectly sensible. But it also has a static mesh refinement, not adaptive mesh refinement, but we statically refine the mesh so that we don't have the Courant hit in the center because we're using spherical polar grid. This is similar to the hammer approach that you saw in the poster, perhaps. It has the approximate general relativity. It has the multi-group velocity-dependent approximate relativity, including this static mesh refinement. As a result, it also has the redshifts of the radiation due to the GR. As a result of these developments, the code is 5 or 10 times faster than previous codes that have been fielded. It also handles inelastic scattering, various sorts, which is important in the energy deposition, and it has various detailed neutrino processes included. Already published are these papers from Fornax. It's a list that has evolved and it now is almost exclusively just looking at 3D simulations. Because of Fornax and the incorporation of the necessary realism into the code, we're able to do many simulations. These are simulations that have already been performed. These are the masses from 9 solar masses to 25 to 29 solar masses, multiple 19 solar mass models, et cetera, to go in various directions in parameter space. The default resolution in radius is 678 by 128 in theta, 256 in phi. We've also done a resolution study, which I'll report on. And we can do about 50, we have done about 50 2D simulations. It was the case 10 years ago, you could do 1 or 2 a year in 2D. So again, there's been significant progress in no small measure due to the development, on the one hand, of the algorithms, the code, Fornax, and on the other, the availability of significant HPC resources. Most of these simulations are being done on blue waters right now with significant support from Theta. So we've done the standard code tests. People will recognize these sorts of things. Hopefully I can advance. This is the Villisca One Trough test. The only thing you're supposed to notice here is that it stays along the axis. These little bubbles go off to the side. And for an unsplit code, if it deviates at all, the code is not good. And this is a standard Rayleigh-Taylor test for the code. We've done all sorts of code tests. This has been published in Skinner et al. 2019 for people who are interested. Here's an example of the mesh. And, you can see how it de-resolves as it goes up to the phi axis in theta. And as you go into the interior, it de-resolves as well, trying to keep the aspect ratios approximately constant so that we don't have the Courant hit at the center. The scaling is almost perfect. This is a scaling on KNL, but the scaling is very similar on blue waters. There are a couple of sweet spots, but by and large, we get 95%, 90% efficiencies up to about 130,000 cores. And we haven't tested it beyond there, but we have no reason to believe it doesn't scale very well up to 256,000. One of the things that part of the science that's very important is that there is a progenitor mass dependence to the outcome. So we are limited by the progenitors we inherit from the stellar evolution community. That is still in flux. But what we right now understand is for a given progenitor structure, densities, et cetera, we know how it's going to explode or whether it's going to explode. That is a new development. The density structures are crucial, and I'll show you an example that how they haven't converged from different groups. The same model, the solar metallicity at 15 solar masses, has a density profile that is fairly different. So what we can do theoretically as supernova theorists is look at what these profiles map onto in the explosion realm, and we've done that. Okay. One thing to cautionary tale is in one set of progenitors that's available, they have a 14.99 solar mass model, a 15.00 solar mass model, and a 15.01 solar mass model. The 15 solar mass model doesn't explode. The 14.99 does. The density profiles are fairly different. And so, again, the mapping between progenitor mass, which is a function of the stellar evolution, and the outcome through the explosion it depends on the unconverged stellar evolution. Now, that may sound like we're blaming another community, but it's true. Now, we've done resolution studies. This is just an example of a low resolution wedge in the inner 60 kilometers, medium resolution, high resolution, and the low resolution calculation of this 19 solar mass model did not explode. But as you keep everything else the same and just change the resolution, it explodes. And that's just the radius versus time as an example. This is an example of low resolution, medium, and high resolution. This is a slice. You can see the increase in resolution. The crucial aspect, and there's some details here, is this red curve to blue curve comparison of high resolution to low resolution. This is the Reynolds stress. The Reynolds stress versus radius. And as you go up in resolution, you get better coverage of the Reynolds stress itself, and that Reynolds stress is crucial to reigniting the explosion. And so there's a resolution dependence, which you can see in the literature, which is code dependent, that has to be resolved. The good thing is, as you go up in resolution, keeping your physics the same, you get more explodable. If it went the other direction with your same physics is wrong. So that's a good development. And this is just comparison of The low resolution, intermediate, and high resolution simulations, when these things get smaller, that's just the zoom. The highest resolution exploded earlier, more energetically. And this just shows the basic structures. And this is on the archive. So I want to compare 2D and 3D first. This is a 2D simulation, exactly the same with the 3D simulation. The 3D exploded earlier. It did not slosh up and down. That's more or less an artifact of 2D. And you'll see it explode earlier. So there's a cautionary tale there. If you trained yourself on this, you have to retrain yourself on this. So here's a 9 solar mass model. What we've been able to do is simulate this 9 solar mass model until everything stops evolving. We can do that with a 9 solar mass model because things stop evolving quickly. And what we've seen is for the lowest mass progenitors, you can evolve for hundreds of milliseconds and then everything stops. You get the energy, you get the mass of the neutron star, you get the recoils, everything is stopped. So we can do the entire simulation. As you go up in mass to 16, 20 solar masses, 25 solar masses, you have to evolve for significantly longer. It's more expensive. And in the short term, we decided to do many simulations to understand the full panoply of possibilities. And we don't have 2 and 3 and 4 second simulations. That's the next shoe to drop. But those simulations for the massive stars are showing the energy is ramping up to 10 to the 51 ergs. And that the energy of these lowest mass explosions is generally, on average, lower, some multiple of 10 to the 50 ergs. And that's consistent with observations. This is a similar explosion of a 16 solar mass progenitor. This was actually done at NERSC on Cori. And the color is the electron fraction. And the deep purple is just below 0.5, which is a little bit neutron rich. And you'll see the red is above 0.5. Oh, that's about 0.5, and the blue is at 0.5. I want to show you the general structures. What you see is bipolar explosions. So you have 2 big lobes. You also see accretion simultaneously with explosion. In 1D, when you explode, the accretion stops, and the accretion is one of the sources of power. And so the multi-D enables you to break that symmetry and have accretion at the same time you have the explosion in other directions. That accretion will keep the explosion going, and it's one of the central facets of multi-D. You can have simultaneous accretion and explosion, which you can't have in 1D. And so that's a central result. This is a similar example of 25 solar mass model. That's the shock wave. That sphere in the center is the protoneutron star. Green is low entropy, and watch the entropy evolve. It gets hotter into the red. That's what the neutrinos are doing, and when it gets high enough, in the particular context, it explodes. You get this many plumes and tendrils, but you can get simultaneous accretion and explosion. You get a dipolar-like structure. And this is the 9, the 10, the 11, and the 12 solar mass models. Each one of these models taking about 10 million, 15 million core hours. And these all explode. 9, 10, 11, 12. The morphologies are similar in some senses, different in others in detail. But all the explosions are fairly similar. Very few are at all spherical. Simultaneous accretion and explosion. Bipolar structures. But not everything explodes. And so if you look at the whole progenitor suite, this density profile for the 13 solar mass model actually, in our code, at reasonable resolution, did not explode. That is not an indication that the 13 solar mass shouldn't explode. It means that it's less explodable, maybe at higher resolution, maybe with slightly different physics, maybe with a little bit of rotation. That remains to be seen. But the default model isn't as explodable. But you also do see some interesting phenomenon. That's the spiral SASE. What we see when the models do not explode is that the SASE comes into its own. When they do explode, the SASEs almost never manifest. The SASE is an instability that doesn't generate entropy to a great degree. It's subdominant in the explosion context. It is there on occasion, It's of interest, but the neutrino-driven convection really dominates. That's where you get entropy generation of not 1 or 2, but 10 or 20 units. That's where you get the real energy deposition. And in our simulations, almost universally, you see that this effect happens only when things don't explode. That doesn't mean that we've carried out all the possibilities. And we see this in a few models. You can get the PNS masses, the masses left behind of the neutron stars, from about 1.3 solar masses to about 2 solar masses. That's the observed range. You can look at protoneutron star development. That's the object that's going to be left behind, and this is just the radius of that protoneutron star. It's the case that in all these calculations, in all this context, that neutrinos are copiously emitted. They're emitted anisotropically and different in directions, and they are the dominant loss channel for the supernova. As was mentioned in the previous talk, the detection of neutrinos would be wonderful. We've detected them only once in the first example of multi-messenger astronomy in 1987 with 87A. But with the detectors that are available now underground and under ice, we will have not 19 events from the Large Magellanic Cloud, but something in our galaxy will generate thousands of events. And you'll be able to watch in real time the internal dynamics. You'll see the shock oscillations. You'll see the core oscillations. You'll see the explosion in principle. Here are the luminosities versus time. This is up to about 0.7 seconds in this particular realization. These are average energies. The thin curves are the 2D simulations, which are much more noisy. That's just what happens. The 3D on average integrated over the 4 pi steradians is almost exactly the same on average, but is much more tame. And this is for a subset of the models. We've done about 20 3D simulations so far. This is HDMI. Unfortunately, it doesn't map well for some of the movies. So let me see. Okay. So gravitational radiation signatures are also important. What we've been able to determine is that these are not just bursts of gravitational radiation that is stochastic. The amplitudes are stochastic, but the underlying frequency structure is predictable. And what you're seeing is these material falling back onto the core, exciting the core fundamental modes of oscillation. So the observation of gravitational radiation is the observation of astroseismology of the neutron star at birth. You can see, again, these are the metric strains in some of the models, and this looks very noisy. But if you do spectrograms, you see much of the power is in particular modes that you can calculate in spherical symmetry for those progenitors. And we can just overplot that. This is the F mode of the oscillation of the core, classical astroseismology. And unfortunately, there's sound here. I'm sorry I didn't mention that in advance. But you'll see that these things look as though they're fairly noisy, but if you actually do a sonogram of these things, it's always the case for every single model, the frequency goes up with time. It's also the case that to get the gravitational wave signals fully, you have to simulate for a fairly long period of time. A lot of the literature does it for the early phases, maybe 300 milliseconds. And if you do that, you might get 10 to the minus 10 solar masses radiated in 3D simulations. You get more in 2D, but 3D is what you have to look at. So the 3D simulations of the solid curves. If you simulate for longer, you see these jumps. So people have been publishing this. You need to publish that. And so the emission of gravitational radiation is not 10 to the minus 10 solar masses, but 10 to the minus 8 solar masses. And the distance out to which you can look goes as the square root of that. So that makes a huge difference. The entire galaxy is accessible. Unfortunately, it's not the local group. That would be another generation of gravitational wave detectors. The other thing that's important is that you would need to calculate the full frequency content of the signal, because much of the energy is at high frequencies, and a lot of people have dumped things at kilohertz or at half a kilohertz, and LIGO dumps it at 16 kilohertz, and that's what we did. We dumped it at 16 kilohertz, it's Nyquist at 8 kilohertz, and that covers all the power effectively. And so you can get all these signals. These are 3D signals from 9 solar masses to 60 solar masses. By the way, our 60 solar mass explodes. And these are the spectra compared to the advanced, this is the advanced LIGO, and here's the Einstein telescope. And you see there's a lot of power at high frequencies that you lose if you don't dump often enough. So what is the current status of supernova theory? I've been working on it for far too long, invested a lot of my blood and time, but I am more optimistic about our capacity to understand supernova theory than I've ever been. It's because of the new capabilities represented, for example, with Fornax, but also the new resources that are available. And we couldn't have done that huge set of simulations if it weren't for Blue Waters and the InSight allocations. So the basic capacity that has emerged is we can do multiple 3D simulations with the necessary realism on the resources available per year. So we can make mistakes. The things are fairly close to critical, and so there are some subdominant interesting processes that need to be incorporated. We have to understand the neutrino physics just a little bit better, but it's MEV physics, so it's basically well in hand. I can talk a little bit more about that. But you have to be able to handle the turbulence well. You have to have decent initial models, and those are still in flux. You can do those models at the last stages in 3D. And so we want to inherit 3D simulations and do 3D modeling subsequently in the baton pass to the supernova theory. And we're in process of doing that. And so that's a very interesting development. There's also convection in the very interior. It's called protoneutron star convection. It does have an effect. There are seed perturbations having to do with the perturbations. That is also of issue. But what I want you to understand now is everything seems to be converging and going in the same direction. That every new thing that we've been able to incorporate at reasonably high fidelity, physically as well as numerically, is aiding explosion. And so most of the models are now exploding. Many of the lower dimensional models, at least broad outline, that are being generated around the world are similar. There are differences which we think we can understand because of the difference in the approaches and also because of the stochasticity and the chaos of the turbulence, which is actually part of nature. An individual progenitor will have, in the real world, in the real universe, will actually explode in multiple different ways because of the stochasticity. That is nature, and it's going to be a distribution function of outcomes. We have to be aware of that, and that's one of the problems and joys of this subject. But thank you very much for your attention.